Hello and welcome to this clip on stereoisomerism in transition metal complexes. We'll briefly look at how stereoisomerism is applied to transition metal complexes, and we'll take you through how to draw the stereoisomers of transition metal complexes. The clip will assume that you're already familiar with Sis Trans Isomerism and the definition of stereoisomerism from your first year available chemistry. And it'll also be assumed that you've done the basics of transition metal chemistry, such as what a ligand is, the formation of coordinate bonds between ligands and the central metal ion in transition metal complexes. So before we start talking about the shapes of complexes, I'm going to assume that you're familiar with the common molecular shapes from your first year of the course. So I'm just going to plough on assuming that you know about all of them, as opposed to having to stop and review them. If you're not sure about them, it might be worth going back over your first year notes and refamiliarizing yourself before we go any further. So octahedral complexes happen when the maximum of 6 ligands surround the central metal ion. They have 90-degree bond angles throughout and a coordination number of 6. So tetrahedral complexes occur when larger ligands surround a central metal ion. So there's only room for 4 ligands instead of 6. These complexes have bond angles of 109.5 degrees throughout and have a coordination number of 4. So the smaller ligands that can form octahedral complexes would be water, ammonia hydroxide and cyanide. However, larger ligands that we come across at A level would be halides. So what happens when a halogen atom receives an extra electron to become, for example, Cl-? The halide ion then experiences repulsion between its electron shells, and they move away from each other. So what happens is the radius of the ion is much bigger than the radius of the atom. So only 4 of these can fit around a central metal ion, and therefore form a tetrahedral complex, as opposed to 6 fitting round and forming an octahedral complex. And the final type of complex you'll come across is called square planar. They're flat and square in shape, hence the name. They have 90-degree bond angles throughout. So the screen now shows a short summary of what each of the 3 types of shapes look like and what bond angle you'd expect to find. There is a shorthand way to draw bidentate ligands in complexes. What you can do is to draw in the atom or atoms, in this case, that possess the lone pairs that are involved in coordinate bonding. And you draw a curved line between them. So if you look at the rather complex looking structure at the bottom of the screen, you'll see there's 2 ways to draw it. And the simplified diagram would make it a lot easier in exam questions. Why don't you pause the video, grab a piece of paper and see if you can do something similar for the 2 versions at the top. Don't worry about the cis and the trans, I'll talk about that in a moment's time. So I'm doing the cis version here, and I've only partially finished it because I wanted to show you how to do it. You start off by drawing in the oxygen atoms, and then you can draw the remainder of the ligand molecule by just a curved line. So now I'm going to show you the trans version. And the first thing to notice is that the water ligands are placed differently, aren't they? So if you look at the trans version, you'll see what I mean. And I've just highlighted them there to draw your attention to them. So again, I draw in my dashes and my wedges to represent the 3-dimensional structure. I add in the oxygen atoms that possess the lone pairs that are involved in coordinate bonding. And then again, I can draw in the curved line to represent the rest of the molecule, which I've now highlighted just so you can see what I mean. So this could be an easy way to draw bidentate ligands in complexes, and in mark schemes it's generally acceptable. In order to explain stereoisomerism in transition metal complexes, it's worth just reminding ourselves about what stereoisomerism is. While we're at it, we can have a look at Cis Trans Isomerism And you'll notice that the way I've defined cis trans isomerism in transition metal complexes is slightly different to the way in which you'd have learnt it last year when it was applied to carbon-carbon double bonds in alkenes in organic chemistry. Obviously there's no carbon-carbon double bonds in transition metals, so we have to think about it a slightly different way. So let's start with cis trans isomerism. First of all, you can see it applies to different shaped complexes and also different combinations of ligand types. But the important thing to notice is that each of the isomeric pairs have the ligands in opposite orientations around the central metal ion. So let's now look at an example of optical isomerism. So this complex has a central metal ion, nickel 2+, with 3 neutral bidentate ligands. And it's octahedral. If you look at it closely, you'll see that the 2 optical isomers are actually mirror images of each other. This is the way you can tell if you've got optical isomerism in a complex. If you've got 2 complexes there in front of you on a page, and they are obviously mirror images of each other, provided it's octahedral complexes, or octahedral in shape, and it contains 2 or more bidentate ligands. They don't have to be different bidentate ligands, they can be the same bidentate ligand. Then you get optical isomerism. So let's look at a case where the bidentate ligands are different. So let's start at the beginning. I've drawn deliberately quite a complex ion or complex molecule to illustrate how it can be simplified. I've done it in displayed form, so you can see how drawing out the displayed form of the ligands can obviously make the diagram start to look quite crowded. So there's no charge in this case because the ethane dioate ion, which is drawn in red, has a 2- charge. So the central metal ion, nickel 2+, the charge is counteracted or negated, so the overall the complex is neutral. So the first thing I'm going to do is to simplify my diagram. I've drawn in the central metal ion. I've drawn in the atoms on the bidentate ligands that have the lone pairs that are involved in coordinate bonding. And now I've drawn in the curved lines to represent the part of the bidentate ligand molecule that doesn't need to be drawn in displayed form. I'm going to draw a dotted line, and that dotted line represents the mirror, the imaginary mirror where you'd see the mirror image. So now I put in my mirror image, and now I can add the curved lines to represent the rest of the molecule in the case of each bidentate ligand. And now you have your 2 optical isomers drawn in 3 dimensions. In the types of questions that you're likely to do on this, they will ask you not just to draw it, but to put in the bond angles as well. So it's always a good idea to add one of them. It doesn't particularly matter where you add them, but provided you put 90 degrees in somewhere, just to show that you understand that it's an octahedral complex and it's got 90-degree bond angles throughout. So we can get different types of stereoisomerism. We can either get cis trans or we can get optical. For it to be optical, you have to have a mirror image that are non-superimposable over each other. So let's start with our octahedral shape. I've put the central metal ion in, and I've put the bonds placed around it to give the octahedral shape with 90-degree bond angles throughout. So let's now add 2 monodentate ligands. If we complete it using 2 bidentate ligands, we now have optical isomerism. The 2 optical isomers are non-superimposable mirror images of each other. So for optical isomerism to occur, you must have an octahedral complex with 2 or more bidentate ligands. But if we change the positioning of the water ligands, you'll see that in one version, I haven't added any other ligands yet, in one version you have the water ligands 90 degrees apart, and that's the cis isomer, and in the other isomer, the trans isomer, you have them 180 degrees apart. So in this arrangement, if you look at them very carefully, they're not optical isomers, because the arrangement isn't a mirror image. They're not non-superimposable mirror images of each other. Technically, you could even have other monodentate ligands in random positions. They don't even have to be bidentate, provided one pair of ligands have the cis trans arrangement as highlighted by the two water ligands drawn in red. So there are three different scenarios where you can find cis trans isomerism in complexes. The first one is an octahedral complex with a coordination number of 6 and two different monodentate ligands. The second scenario is an octahedral complex with a coordination number of 6 and both monodentate and bidentate ligands. And the third scenario is a square planar complex with a coordination number of 4 and two different monodentate ligands. And the key thing to look out for cis isomers is the same ligands are 90 degrees apart, and for trans isomers the same ligands are 180 degrees apart. So an example of transition metal complexes in medicine would be cisplatin. It's used in chemotherapy for the treatment of cancer, and it unfortunately has a number of side effects on healthy cells, including affecting the nervous system and the sense of hearing. What it does is it interferes with the ability of the DNA in cancer cells to replicate, and therefore prevents the malignant tumours from increasing in size and spreading. But although it's very effective at doing this, it's also very effective at affecting healthy cells, and that's where the toxic side effects come from. So we looked at EDTA very briefly earlier in the clip, and mentioned that it was a multidentate ligand. Ligands such as EDTA are able to physically wrap themselves around toxic metal ions in polluted streams and rivers, indeed in the bloodstream. So for example, it can react with mercury in the bloodstream to render it incapable of reacting with or interfering with biochemical processes which the mercury would otherwise do. Same for lead and same for cadmium. An example of an equation showing this reaction would be at the bottom of the screen. So as well as medical applications, it would have environmental applications after a waste spillage. For example, if you had some heavy metal spillage from a factory that needed to be cleaned up to avoid pollution of the environment, you'd use chelating agents to do this job for you. So let's now have a quick look at a couple of exam questions on stereoisomerism in transition metal complexes. So in this question I've crossed out the second and third part because they're to do with the reactions of transition metals, which is covered separately on another clip. We can do the first part because it talks about the shape. Now the thing to think about here is the size of the ligands. So if we recall, we said that water is a small ligand and chloride is a large ligand. So small ligands can fit 6 around the central metal ion, and large ligands can only fit 4 around the central metal ion. So that allows us to put octahedral for hexa-aqua cobalt and tetrahedral for tetrachlorocobalt. So it might be worth, if you can't remember it easily at this point, getting your flashcards out and doing a flashcard of the relationship between the number of ligands that fit around the central metal ion and the shape that it gives. So large ligands only fit 4, which gives tetrahedral. Small ligands fit 6, which give octahedral. And you can put some examples down as well to help you remember it. So let's now move the page down You can probably see at the bottom of the screen it's starting to ask about stereoisomerism. So you can see already that it's quite a big question, isn't it, really? Because there's 8 marks on offer. So it gives you the chromium 3+ ion, and it forms a complex ion of formula CrC2O42 and then H2O2-. And there's no getting away from it. You need suitable diagrams. So let's do what we did earlier and draw out the central metal ion. Okay, let's now look at the ligands that we've got. So you've got the ethane dioate ion, which is bidentate, and you've got the water ligand, which is monodentate. So the first thing I do is I draw out the octahedral shape. So what I can do is I can put the water molecules top and bottom, for example, or I can put them in any 2 positions I want. But what I need to remember is that the bidentate ligands will have 2 places where coordinate bonding will take place. And I complete it by drawing the ligands in any particular order, doesn't really matter. I can use the shorthand version to make it easier to demonstrate to the examiner what I'm talking about, and I make sure it's in square brackets with a negative charge. And I put in the mirror image, and to emphasize that I do a dotted line between the 2 isomers, like so. And I state what type of optical isomerism, or what type of stereoisomerism I am demonstrating with these 2 diagrams. So not forgetting that stereoisomerism also includes Sis Trans Isomerism. I've done 2 versions now that show the cis and the trans isomers. And I've labelled them as such so the examiner can tell what I'm talking about. But what I still haven't done is explained what stereoisomerism actually is. So to do this, I'm going to make some more space for myself and move the page down slightly. So I've given a definition of stereoisomerism, I've given a definition of optical isomerism, and just for good measure, seeing as it's an 8-mark question, I've said that octahedral complexes have 90-degree bond angles between ligands throughout. So it's obviously quite a lot to include, but it is a long answer question. They did ask you to use diagrams, and the idea of stereoisomerism does leave it open to not only optical isomerism, but also cis trans isomerism. So it's important that both of those are brought into your answer. And we also need to make one more mention of the bond angles, the angles between the ligands in the cis trans isomers. And that is that the H2O ligands are 180 degrees apart in the trans version and 90 degrees apart in the cis version. So this one I'm actually not going to do, because I've just done one like it, and I thought what I might ask you to do is to grab a piece of paper, pause the video clip, and see what you can come up with. When you press play on the video clip again, I'll take you through the suitable mark scheme for this particular question. But bringing it down, it's another 8-mark question, but quality written communication using the correct terminology is an extra mark, so it's 9 marks. So because it says suitable examples, there's more than one suitable example I could use. So instead of going through every single suitable example and just feeding it to you, it would probably be a bit better for your learning to pause the video and see if you can have a go at this yourself. And then resume the video and see what a suitable mark scheme might look like. So I would allow yourself around 10 minutes to do this piece of work, but it would be a good example of whether you've taken your independent learning and your notes that you've made on transition elements so far and can apply them to a slightly more challenging and open-ended application style question. So for the question that we looked at, we correctly identified what a stereoisomer was, and we drew cis trans and the 2 optical isomers. We got a mark for each of our versions. We had the water at 90 degrees in our cis, and 180 degrees in our trans. We also mentioned that optical isomers are non-superimposable mirror images. And we had the word optical, cis trans, rotate, plane polarized. That means there's 3 of those needed. We used 4, so that got us a mark there. Now I'm just wondering where we got our 8th mark. Yeah, it was here, sorry, for giving the correct angles between the H2O ligands. That gives us 8 in total for our answer. So now let's have a look at your version, because I asked you to have a go at that other version. I left it blank for you to have a try. So, without actually talking through it, what I'd like you to do is to take your answer and see if you can mark it yourself. Try and be honest and strict with yourself. What I suggest you do is bring your attempt in perhaps to a subject extension at college, or maybe share it with your teacher. You can take a photograph perhaps from your phone of the screen and have the question handy to show your teacher and see what they think. But otherwise, hopefully this has been a useful introduction to some of the various aspects of transition metals. Like I mentioned in passing on one of the previous screens, the actual chemical reactions of transition metals are a separate clip, because obviously there's quite a lot. This clip is quite long, as you can probably see. But in the meantime, thanks for your time, thanks for your work, and do come in and have a chat with one of us if you've got any questions so far. But in the meantime, I'll see you soon, and thanks a lot.